Alrighty. I want to take something that you've done in physics already and compare it to calculus and how we do it in calculus. The results are exactly the same. But the approach... You know, if I would have waited, it wouldn't have rang. The approach that we use in calculus is different than the approach that you probably used in physics. So, for instance, have you seen this formula before? Now, maybe you saw it as negative 9.8 because you did things in the metric system in physics. But that's the position function. I'm going to do it in terms of feet instead of meters because the book does more things and the AP test usually does more with feet. I don't know why. Okay. But in physics, did you talk about where that came from, or were you just given a formula and then you play with that formula? Given it. Okay, so what is, first of all, what T is time? What's V naught? Initial velocity, and S naught?
Initial placement.
Oh, initial placement. Okay, so for instance, you're on a cliff above a river. And you happen to have a bowling ball. Why you have a bowling ball on the top of a cliff, I have no idea. But you're going to throw that bowling ball down into the river. And we're going to throw it down at a speed of negative 10 feet per second. And how tall is the cliff? 100 feet. Let's not go 100, it's too close to 10.
102. Still close to
500? Ooh. All right, that sounds fun. 500-foot tall cliff. So somehow you got on top of a 500-foot tall cliff with a bowling ball. So in calculus, what we do is we work backwards. And the reason I want to do this today is because they are starting to show up in problems, but it also is something called a differential equation, which we've started hinting at a little bit. And this is probably one of the more common applications of a differential equation. So what do we know? One of the things we've talked about before is that if we have the acceleration, we can find the velocity. Actually, let's go the other way. Let's start with the position function. If I have the position function, I can get the velocity function by derivative. And then if I take the derivative of the velocity function, I get the acceleration function. Okay, that's a derivative. What we've also talked about and done a little bit of work with is going the other way. Okay, so if I take the integral of the acceleration, I get the velocity. If I take the integral of the velocity, I get the position function. We're going to combine all that stuff together, and when we're done, we will have the formula for this scenario over here. So one thing that I know is constant is the acceleration due to gravity is negative 32 feet per second squared. Right? Acceleration due to gravity is negative 32 feet per second squared. And I'm going to use that and some calculus to end up with the formula that we need here. So I know that if I want the velocity, I can take the integral of the acceleration, which in this case is the integral of negative 32 dt. Don't forget that dt. It's very important because it tells you what your variable is. Okay, what's the antiderivative of negative 32? Negative 32t plus c. Good. Indefinite integral must have a plus c. And as I said, that is the velocity graph, or velocity function, I should say. Now there's a big problem there. We've got a plus c, which means I just generated an infinite number of answers because c can be anything. The differential equation part of this problem is going to allow us to go from an infinite number of solutions down to one and only one solution. And that is by solving for t. How do I solve? Sorry, not solving for t, solving for c. How do I solve for c? What do I know?
your velocity is negative 10 meters per second.
When?
Right when you drop it.
T equals 0.
When t equals 0. Good. So I'm going to get negative 10 feet per second when t equals 0. So therefore, c equals negative 10. I'm assuming you can all take negative 32 times 0 and get that. Which means my final velocity equation for this problem is negative 32t minus 10. How are we doing so far? Hot diggity. Use the robot hand, slide this puppy up, change colors. Let's go with blue. Now, if I want the position function, I can take the integral of the velocity function, which in this case would be the integral of negative 32t minus 10, and don't forget that pesky little dt at the back. What's the antiderivative of negative 32t minus 10?
Negative 16t squared minus 10t.
Plus c. Got to get rid of that crazy little c. What do I know? What's the position at t equals 0? Most of the time, by the way, you will use t equals 0. Sometimes not necessarily so.
500.
Yeah, 500. We know that before I did anything, when t equals 0, I was 500 feet off the ground. So 500 is equal to negative 16t squared. Whoops, not t squared, I lied. 16 times 0 minus 10 times 0 plus c. So again, nothing exciting here. We know that c equals 500. So you're saying to yourself, why am I doing all this work when I know the answers already? Because in physics, we just plugged and chugged. You told us in the beginning of the problem that the initial velocity is negative 10. The initial height is 500. Why can't I just plug and chug? You can. But I wanted to show you where the calculus comes into play, and therefore s of t is equal to negative 16t squared minus 10t plus 500. Okay. For this particular problem, that's what you would get. And again, in physics, you're given a formula, you understand what the components are, you plug in the necessary components, and you solve. In calculus, it gets a little bit more difficult because not every problem we're going to solve is going to be a velocity and acceleration and a position problem. They will change up. Or you might be given different information. Maybe you don't know information at t equals 0. Maybe you'll know information at t equals 2. So after 2 seconds, you know how far the bowling ball is above the ground. And I'm almost sure that in physics you played with all kinds of different scenarios here, right? Like, for instance, if I open up the window and throw Christian out the window, we could calculate how tall we are off the ground if we just time how long it takes him to get to the ground. You did those kind of things, right? Yeah. So I don't want to go into those problems, but that's what these formulas will allow you to do. And we've dabbled in that a little bit with the diver off the diving board. What if, let's go back to the initial problem here. What if I didn't throw the bowling ball down? What if I just dropped it? What changes?
Velocity.
Keep going. What about it?
It'll start at 0.
Good. Initial velocity will be 0, so that middle term drops out. What if instead of throwing it down, I throw the ball up to start?
Positive velocity.
Positive velocity, right. So it's just plugging and chugging different numbers into that equation. Okay? Questions? Standing. Okay, let me hide this and stop this.